Hi, in this video we're going to take a look at how we can use calculus to find the area underneath a curve. Some of the reference material you see on the next few slides comes from the textbook Mathematical Methods Dimensions, Units 3 and 4, published by Pearson Longman in 2005 in Melbourne. Now we're going to use what's known as the fundamental theorem of calculus. It's a theorem that relates the area under a curve to integration. As such, we'll use it to derive it to use using the area under a curve as an example. So, in the diagram shown there, let's say that we want to find the area under the curve bound by the lines x equal to a, x equal to b, the curve itself, and the x-axis. We want to find the exact area. Now, let the area in question we want to find to be A, and let's say the delta area is a very small increase in this area, which is shown in the diagram. Now, there are three distinct areas I want to concentrate on. Firstly, you've got the area which is underneath the curve. So one point corresponds to the curve. So we've got E, M, G, F, which is this rectangle down here. We've got the area itself, the exact area, delta A, which is E, H, G, F, which is shown here. And then we've got the rectangle which is above the curve, noted by N, H, G, F. So these three rectangles are shown here. Now in the first case, the smaller of the rectangle, you can see that the delta A is larger than the first one, but smaller than the second one. Now for the first rectangle, it's got a side, this length here would so x is the coordinate of that point, that this corresponding point then would be the y coordinate of it. So its length then is y, and its width is delta x. So its area then is y times delta x for the area of a rectangle. Now, the actual area delta A is essentially a trapezium, as we can see here, and the larger rectangle still has the same width, namely x. But if we take this point MG, you can see is the same as EF, so it's y. So this smaller increase then between M and H will take as delta y. So its side length then is y plus delta y. So its area then is effectively delta x times y plus delta y. So as we can see, the first one, which is y delta x, is less than the actual area delta A, which in turn is less than the larger of the rectangle, which is delta x times y plus delta y. So if I divide by delta x, we'll end up with y is less than delta A over x, which then is less than y plus delta y. Now, as x gets smaller, approaches 0, delta y is going to approach 0 as well. So if I just demonstrate that, here the black line represents y plus delta y, and if I move it to this point, delta y is the length up from EM to the curve, so you can see it's shorter than what it was there. So if I move it across to here, it's getting shorter again, so delta x now is smaller. So as delta x is getting smaller and smaller, so too is below the dotted line and the curve, which is delta x. So when we're basically on top of each other, delta y, you can see, is getting smaller and smaller. So we can say then that y plus delta y is approaching y, so therefore what we've got here then is as delta x approaches 0, we've got the limit of delta x greater than approaches 0 of delta A over delta x is less than y. Now it can't be less than both, so therefore a conclusion must be that in the limit, this becomes dA dx is equal to y. So since y is equal to f of x, that was the equation of the curve, we can write down then that dA dx is equal to f of x. So when we take the antiderivative, we can write down then that a is equal to the integral of f of x dx. Now we know that when we take the antiderivative, so capital F of x means it's the antiderivative of f of x, and we know that it's equal to a constant. So therefore we can say that the area is equal to f of x plus c. Now, when x is equal to a, the area is equal to 0. So in other words, when we simply got x equal to a, we've got a vertical line, no width, so therefore there's no area. So we can substitute those in, and that gives us therefore that c is equal to negative fa. So we've now got that a is equal to f of x minus f of a. Now when x equals b, which would be over here, that would represent then the entire area. So when x equals b, the area under the curve in question is this part around here, and that is the exact area. So we can say that when x equals b, a equals the exact area going from a to b. So the exact area is equal to f of b minus f of a. So in other words, the area bound by the curve, the x-axis and the two lines x equal to a, is given by f of b minus f of a. So in other words, we're saying that we can write that as we find the integration between the 2 points a and b, that is equal to f of b minus f of a. This is called the upper limit of integration. This is called the lower limit of integration. So the fundamental theorem of calculus says that if the function is continuous within the interval a to b, the antiderivative or the integration of the function between the points a and b is equal to x of b to x of a. It's equal to the same as substituting f of b minus substituting f of a. Our integrals where we have limits are what we call definite integrals. And the limits of integration are simply the values, the endpoints a and b, and f of x itself is called the integrand. So finally, just some theorems for definite integrals. If we have a constant inside the integration symbol, exactly the same as if we take k outside. If we're taking the integration of the sum or difference of two functions, that is simply equal to k times the first one plus or minus m times the second. So in other words, it's exactly the same if we work out the integral of each of them and then work out the final result. Theorem 3 says that the integral from a to b is equal to the negative of b to a, and we'll show that with an example in class. And finally, if we go from if c is greater than or equal to a, less than or equal to b, and we're continuous between those 2 points, the integral from a to b is exactly the same as first going from a to c and then from c to b. And again, we'll show an example of that in class. So there we have a quick explanation of how that the area under the curve that's continuous is equal to the definite integral going from a to b.